Hello students, my name is Shashank Shekhar. So today we will start with the chapter coordination compound. So if I look at the syllabus here, so we have first of all introduction part. So today we will see the introduction part of coordination compound. We will discuss about the first theory that was given to explain the coordination compound, that is the Werner's theory. So our today's main focus will be Werner's theory. So let us look at the topics that we have. So first of all, we will give you a general introduction of the coordination compound, and we'll see how does Werner's theory explains this coordination compound complexes. Then we'll move to some experiments that was given by Werner's or that was performed by Werner to examine this coordination compound. After that, we will move to types of valencies. So two types of valencies are there in coordination compound, primary and secondary. We look to that. Then we will see the final postulates of Werner theory and also its verification. The experiment which was done, we will see the actual experiment, how it was done. Okay. So first of all, what is coordination compound? So you know that transition metal, they form a large number of complex compound due to their variable oxidation number, and in that process they get bounded to a number of neutral and say ionic molecule. So this bonding of this transition metals to say anion or cation or say neutral molecules lead to the formation of the coordination compound. Now, why is this coordination compound important? Because this is very important in the field of synthesis. So, various syntheses in organic chemistry have been made easier with the help of this coordination compound, and they provide a more efficient way and a more you can say productive way to produce organic compound rather than our say this primitive method of organic synthesis in which we used only organic compound, simple organic compound to carry out a reaction. So what does this do, this coordination compound do? So they are generally used as a catalyst. So they act as a catalyst and make our reaction faster. Okay, clear? Now in the development of the coordination compound, various concepts have been given to explain the bonding, that how this bonding takes place. So it is neither a kind of ionic bond nor a covalent bond. A new kind of bond has been seen in coordination compound, that is termed as coordinate bond. We will see what this coordinate bond is and help us and see how does this functions and how does this functions. So if I talk about the examples of coordination compound in nature, so we have the example of chlorophyll, so which is found in plants, hemoglobin, which is found in human blood, vitamin B12. So all of this are nothing but a coordination compound of magnesium. So therefore we can say that coordination compound are very important for our survival. Now let us look at the first theory, that is the Werner theory, that is given to explain the coordination compound. So he was a Swiss chemist and he formulated his idea about the structure of compound. For this, he prepared and characterized a number of coordination compound with the help of simple experimental techniques. And in that process, he proposed the concept of primary and secondary valency. Binary compound. So if you take about the binary compound, say CrCl3, in which only two species are present, or CoCl2 or PdCl2, they have only the primary valency. So what is primary valency first of all? So if you look at these three, CrCl3, so CrCl3, CoCl2 and PdCl2. If I ask you to find the oxidation number of all the transition metal in this compound, how you will find it? So we have Cl3, so that is 3 negative, and overall this compound is neutral, and let us assume X be the oxidation number of your metal in each case. So we can write as X minus 3 is equals to 0. So X is the oxidation number of your chromium and we are taking the oxidation number of chlorine as -1. Therefore, or we can write it in this way, 3 multiplied by -1. And overall, it is equals to 0. Next, we have CaCl2, CoCl2. So similarly, here 2 chlorines we have. Therefore, 2 into -1 is equals to 0. And again, for PdCl2, we have again 2 chlorines. So we'll write it as -1 is equals to 0. Now if I find the value of x, we'll get it as 3 in this case, 2 is in this case, and 2 in this case. Now what are we seeing it from here? That this say anions, that is our chlorine, 3 chlorines that are present are counter anions, they are satisfying the positive charge on chromium. Okay, so the one which is say doing the work of satisfying the valency of the metal are termed as primary valency. So they are satisfying the primary valency, and the number of atoms are 3 in this case for chlorine, so -3. So therefore the oxidation state of our chromium is +3. This is +3. This is +2. And this is also +2. So this was the initial, you can say, definition of our compound, the ionic compound. So we treated ionic compound in this way until we were made to see this type of compound which have neutral type of ligands attached to them. So to explain this valency, the second type of valency, he did an experiment. What he did, he treated CoCl3 6NH3. So he took such a compound and treated it with AgCl. Okay, treated it with AgCl. Now it was seen that 1 mole of CoCl3 6NH3 reacted with. So what are we treating it with? We are treating it with Ag. Okay. So in each case we are treating it with Ag. So when we treat it with Ag, the Ag takes the 3Cl. Okay, and gives us 3 moles of AgCl. Next, he took in the series of compound chloride with ammonia, it was found that some of the chloride ion would be precipitated as AgCl. Now if we take example of this one, then again if you treat our say this compound with Ag, then it again gave only 2 moles of AgCl. Okay, it gave only 2 moles of AgCl, although we have 3 moles here, but it gave only 2 moles of AgCl. And we have 5NH3, that is a neutral, that is a different case. Now in the third one, which has only 4 ammonia, so we are decreasing the number of ammonia. Initially 6 moles of ammonia were there, so all 3 chlorine were precipitated. In this case 5 moles ammonia are there, so only 1 mole of chlorine is 2 mole of chlorine is precipitated. Now if we have 4 moles of ammonia, then only 2 moles will be 1 mole will be precipitated. Now if we have say 3 moles of ammonia, it will be 3, then it will give 0 mole AgCl. So we can see successively that as we are decreasing the number of ammonia, the number of AgCl ion precipitated is getting less. So what are we treating in all of these reactions? In all of these reactions, we are reacting CoCl3 dot 6NH3 with water, Ag. So we have seen in this case that we are getting 3 AgCl. Similarly, we are getting 2 AgCl, and in this we are getting 1 AgCl, and at last we are getting 0 AgCl. So what can be derived from this experiment? That only the number of ammonia is decreasing, we can see that the number of chlorine ion that is precipitated as in the form of AgCl is getting reduced. So we are treating it with AgNO3. AgNO3 silver nitrate solution. So how did he explain this? How did Werner explain this? So for this, he said that there are two types of valency in a complex coordination compound. First is primary valency and the second is secondary valency. Now, the primary valency is ionizable. Ionizable means if you dissolve it in water, then you will get the anion part separated from the cation part. So when we are treating with AgNO3, the ionizable valency, that is the ionizable chlorine, which can be ionized, we are getting attached to AgCl and we are being precipitated. And they are primary valency are those which a metal normally exhibit in the formation of simple salt. Now primary valency are satisfied by the negative ions. Okay, primary valency are satisfied by the negative ion. So only negative ion can be the satisfying factor for our metal. Okay, so we have seen this where we have Ag and the primary valency, the ligand which was satisfying the primary valency was Cl minus. Now, Werner proposed the term secondary valency for the number of compounds which are directly bonded to the metal ion. In each of the example of secondary valency is 6. So here is the case. So what we have taken? We have taken CO, the previous example only, and it is seen that the Cl which was not getting precipitated was coordinately bonding to the cobalt ion. Okay, they were not satisfying the primary valency. Instead, they were being coordinately bonded to the cobalt and cation. So therefore, they were not ionizable. So the difference between primary and secondary valency is primary valency is ionizable, secondary valency is not ionizable. Primary valency is satisfied only by negative ions, whereas the secondary valency is satisfied by positive ions. So in each of these example, what happens is that as we decrease the number of ammonia to satisfy the 6 coordinate valency, the chlorine was going into the inner sphere. So this is called as inner sphere. So if you look at a coordination compound, CO, NH3, whole 6, Cl3. So this is the inner sphere or the coordination sphere. We say it as coordination sphere. Okay. Now in the next case, when one ammonia was less, one of the Cl moves to us inside. So you can see here that the bracket term is the one which is satisfying the primary valency, secondary valency. So as this Cl gets inside this bracket due to one less ammonia, now as outcome of this Cl becomes non-ionizable. Okay, this becomes non-ionizable. Whereas the other remaining Cl were ionizable. Again, if we take the next one, we'll take CO, Cl2, NH3, 4. So this it should always have a 6 secondary valency of 6, secondary valency of 6. So one Cl will be left. So these two Cl will be, these two Cls will be non-ionizable, and the one which is outside, this one and this one and in this one, all these three are ionizable. And they are the one which are satisfying the primary valency. Okay, clear? Now here is an experiment, so which we will discuss in more detail later on. So it was seen that on dissolving this in solution, and doing the, say, passing the electricity, the electrolyte ratio was found to be in this fashion: 1:3, 1:2, 1:1, and 1:1. So we'll see the reason of it. Next, this is the one. So we have CO here, the metal ion. The NH3 inside is the secondary valency, which is inside the coordination sphere, and the Cl3 outside is the primary valency. Now, on the basis of this experiment, Werner proposed some of postulates. So the postulates were that in a coordination compound, so if you take a coordination compound, then the metal ion, the transition metal ion, shows two type of linkages. So they are linked to two type of valencies. First one is primary. Primary are ionizable and they are satisfied by negative ions. Second one is secondary. They are non-ionizable and they can be satisfied by positive, negative, or neutral, all of these three. So it is written that primary valency are normally ionizable and satisfied by negative ions. Now if I talk about the secondary valency, they are non-ionizable and they are satisfied by neutral molecules or negative ions or positive ions also. Positive ions are also there. The secondary valency is equal to the coordination number and is fixed. So this secondary valency value is called as coordination number. Coordination number. Now the ion groups bonded by the secondary linkage with the metal ion have characteristic spatial arrangement. This is very important. So if you have studied about ionic compound, you must have seen that ionic bonds are non-directional in nature. What is the meaning of this? That they are not oriented in a proper manner. They are non-directional. They will be just close to your ion and that's all. Okay, the positive ion and that's all. They will not be say organized in a given specific manner. Like we have NaCl, so it is not such that or we can take the example of CaCl2. So it is not such that Cl will be like this or there will be some bonding or bond angle. Okay, they are non-directional. They can be present in any direction such that the energy can be minimized. But if I talk about the secondary valency, they have characteristics spatial arrangement. So if I talk about spatial arrangement, we have seen the example of CO bonded to 6NH3. So this 6NH3 have a spatial arrangement. All this ammonia molecules have a spatial arrangement. In the coordination number of case of 6, it is generally octahedral. Okay, octahedral. So 4 of them are present in plane and 2 are present on the outside. Okay, so this is octahedral. The spaces within the bracket are coordination entities or complexes, where the ions that are outside the brackets are called counter ions. Okay, now what is the verification of these postulates? How do we verify these postulates? So for this, he did this experiment. Okay, he did this experiment. What he did is that he tried to measure the SiC conductivity, the molar conductivity of ionic solution. So it depends upon two things: the concentration of solute and the number of charges. So what he did, he defined the concentration for each of this one. Okay, so he take 1 molar solution, and now the conductivity will totally depend upon charges. Okay, it will completely depend upon charges. So he took the various compound that were found of different colors, and he treated it with he did the conductometric experiment in which he found that the ratio of the our ions was decreasing. So the ionizable, so in this case we have 3 Cl and 1 this. Okay, so 3:1 means the conductivity which was seen after this experiment, it looks like that 4 ions are involved in this, whereas in this case there were 3 ions, and in this case there were 2 ions. So what does this depicted? This depicted that we have say do not have Cl minus present as ionizable one. If they were ionizable, then they would have been taking part in this conduct or increasing the conductivity. Okay, got it? So on this experiment, we can also say that this one has a primary valency ionizable as 6. That means the chlorine that are involved in primary valency are 6. Sorry, primary valency ionizable chlorines, yeah, are 6. In this case, it is 4. Okay. In this case, we have 2. Whereas in secondary valency, it is 3, it is 2, and it is 1. Okay, got it? So this was Warner theory. So what were the main points of Warner theory? He said that 2 types of valencies are there, primary and secondary. The primary valency were ionizable and non-directional in nature, whereas the secondary valency were ionizable and directional in nature. Okay. Now next, in the next class, we will be looking more about this terminology, that what is our say this coordination sphere, what are ligands, what are neutral ligands. So we will see this in the next class. With this, I end my lecture. Thank you.